Yeah, so as everyone else, we have done something federated. But we tried to do this for a music recommendation system. So I am Lukas from Linköping.
And I'm Christian from Linköping. Also from Linköping.
Yangyang from University.
Yeah, so the agenda will be that first we'll talk something about the graph neural networks that we use for the recommendation systems. Then a bit about federated learning in general, and especially FEDA, which we used. On the data processing, and some bit about how we deploy this, or finishing off with some demonstration. Yeah. So.
Yeah, so after the last meeting where we came up with the idea of using some kind of neural networks for recommendation system, we found somewhere that you could use graph neural networks. So we started looking, and we found this lecture titled GNNs for recommender systems, given by from a course at Stanford. And given we have used Reza in his course, I was like, maybe this is a good idea. Turns out it was given by Professor Jure Leskovic. I know a bit about him because I worked slightly with the graph neural networks before. And turns out he also has a course named Mining Massive Datasets, which focuses on MapReduce and Spark. We've heard about this as well. So I was like, this seems like a good thing. So I will start off by summarizing the idea of graph neural networks for recommender systems. So we start with what is a recommender system and how is it modeled. So today it's often modeled as a graph where it will have, it's a bipartite graph where you have user on one side, you have often called items on the other side, and connected is these edges that can be clicks, purchases, reviews, whatever, or just some kind of connection between the user and item. And the task is often to make a link prediction, to create a new link between that doesn't exist in the current dataset. And to do that, you need a score function. Other than this graph you see here, you can also extend it on both sides. So on the item side, you can visualize maybe some kind of categories. Maybe in an Amazon shopping thing, it could be home, kitchen, bedroom, whatever. It could be colors, it could be many other things. And on users, you could have location, other properties about the user, maybe gender, maybe whatever. So they can be extended on both sides, but we will keep it this simple. User item, we can also see that it isn't always user item, but we'll come to that later. So to get the recommendation, you often use what's called embedding-based models. So each user item will have an embedding vector. In this case, it's a real value vector of dimension d. In our case, d is something like 16 to 64, so it's not massive, but it's not super small. And then you use this score function, which take these two vectors, and you will get some kind of score. How good is this connection? And then you can make these predictions to come up with new links between them. So this user will have an embedding vector here. This item will have the same size. And what this score function is, we'll also come to very soon. But first, you need to be able to train these. One of the early version is what's called binary loss. You want more or less, is it a connection or not? But this turned out to not work great for larger graphs because you want what's called personalized recommendations, right? So what you try to do is you try to optimize for each specific user, optimize each edge. So you will have a score function between current user u star and the positive edges. These are the current existing edges. And then you have a subtraction with the current user and all negative edges. So we'll go over all negative edges and you will go over all positive edges. So for this user, you want all positive edges to be larger or better scored than all negative edges. So if an edge between user 1 and item 1 is 2, it doesn't matter if there's the same, if a connection between user 2 and item 1 is higher or lower. It's just for this specific user you want the edges ranked. And you do this to optimize. This is a surrogate loss to optimize for recall. So this is the heaviest map we have here, I think. Not too difficult, hope. So why do they work? Why do the embedding models work? It uses collaborative filtering. So the idea is that if you watch 20 movies at Netflix, your friend watches the same 20, and the friend decides to watch another movie, a good recommendation for you is that this 21st movie could be a good option for you as well. So different, similar users like similar items. And there you use these embedding-based models, and it's important here now that the embeddings aren't too big. If you have a massive embedding vector, you could more or less just one hot between the embedding and the user. So you want to learn some kind of embedding for the user and items. And this you do with the model called LightGCM. So this is a graph neural networks. It builds on graph convolutional networks, where it will send the embedding using the adjacency matrix. So here you stack all the users on top of each other. Here you have all of the items. If there exists a connection between user 1 and item 1, you will have a connection up here. And then you will have the same adjacency matrix, or the connections here will also be apart here. They are always directed in both directions. Yes, so you will have the adjacency matrix, you will have the embedding matrix we talked about. They are all the same depth or the dimension, and then you just stack them on top of each other, and then you update the embeddings according to top right here. You will more or less just take an average or a sum of all the embeddings, and this will be the new embedding for the specific user and item. So what happens is you will have these more or less from layer 0 here, from layer 1, you add them up to each other. Then you will just average it according to this in LightGCM, super simple. Sometimes they value, for example, layer 0 higher than layer 1 so that you retain the original embedding value. And to make these, and this is called multi-scale diffusion when you combine all of these embedding matrices. And to make a scoring and to get a prediction, we use just a normal dot product. If two vectors are similar to each other, it will be a high value, very positive value. And if they're totally opposite, it will be very negative. And then we use the sigmoid on this, so it will be close to 1 or close to 0. And this is the model that we then implemented for the federated learning.
Then I will speak about federated learning and the platform we need to train our model, which is Python. So as we can see in the picture, the federated learning, the centralized learning, require all the types of devices, no matter it's a mobile or anything, to send the local data through the internet and to the data center and train the global model data. So which will cost a lot of network resources. It's not efficient. And then the most important thing is we care about the data privacy. Sometimes the data cannot be able to send, or we don't want to share it. And then for the federated learning, we solve this problem somehow, like by training the model in local and with the local data set, and only transfer the model parameters through the internet and to the global model. And global model basically just in the data center and do the aggregation and then distribute it back to the clients. And then you keep doing several runs. It depends how you set the configuration. And then I will talk about the Federated framework, where we choose, or which we choose to train our model. And then why we pick up this model is because of the following 4 reasons. First, it's flexible. It's flexible and it's highly adaptable to all types of application scenario. For example, you can use it for music recommendation system like us, can do segmentation, can do book recommendation systems, anything you want. And also you can use PyTorch and TensorFlow as you want as well. And second is modular. It's modular by, for example, the model parameters aggregation. And in this way, we can change the algorithm as we want without rewriting the whole project. And third, it supports. It has many provide many different supports. For example, we can use the API dashboard. It's easier for us to view the training process. And finally, it supports the multiple clients across different regions to train the model together and collaborating together, and which is the core of federated learning. So in total, Federated is the best choice of our experiments. Okay, you agree. Okay, so here is the Federated training process, which includes 4 steps. First is client training, the local model training the model with the local dataset and have the model parameters. And then they send the model parameters through the internet to the global data center and to aggregate the model parameters. And that's the step 3. And then step 4, the global model will be distributed back to the client. And then for our experiments, we calculate the communication overhead, which only happened in the step 1 and the step 3. Like when we send the model parameters to the global data center, and then when the global model will be transferred back to the local, and that will cause the communication overhead. As we can see here, it's 10 gigabytes. And for our data set, it's 1 gigabyte in total. And then each client will have 20 megabytes music playlist. So we have 51 clients. And then for the model size, it's 100 megabytes. So there will be 100 multiplied to 51. And so as we can see, there is a potential communication issues that it will cost a lot of network resources for that. But the most important thing is that we want to evaluate the feasibility and the efficiency by using Federated to do federated learning. So we already achieved our purpose. And next step, we're gonna optimize the model size in many different other ways. Okay, and then here is our experiment architecture. I will explain it from 2 aspects, geographical and logical. So we have 3 data centers, 4 data centers. 3 are located in Linköping as 3 computer rooms, and then 1 is located in Umeå University. So the seed model, global model, is located in Uppsala. So the client train with their own local dataset and then send the model parameters to the Uppsala, and then Uppsala aggregated all the parameters and distributed it back to Umeå and Linköping. And then here is the logical architecture. And then the global model, Uppsala received the parameters and aggregated, distributed back to 3 rooms, and another room, Lu, is in Umeå. And all of them have a different local data set and then train their own models. We set it as 1 epoch. It doesn't require to train so many to keep the data features, and then just do 10 rounds. Here is the experiment configuration. Another good thing of our experiment is we have a variant hardwares, and some computers has CPU only, some computer has GPU, but it proved that we can make this federated learning model work in the heterogeneous environment. And we have our dataset saved in Google Cloud, and all of the computers are Linux. They have a variant configuration. We have 51 clients in total, and this is the prerequisition for the federated model and versions of Python. And for the hyperparameters, we use the standard configuration. Learning rate is 0.001, and epochs is 1 epoch for local machines, and round is 10 rounds in total. And then my colleagues gonna introduce the dataset.
Yes. I might also add that we had a better experience in Federated than the first group. The data set, we decided to use 45 million playlist dataset, which is a set of 1 million playlists, American playlists from the years 2010 to 2018. In total, it contains roughly 2.3 million unique songs, but they occur in more than 66 million different positions in these playlists. And the top tracks this year was Humble by Kendrick Lamar, and this gave us a lot of data to work with, but also manageable, but sometimes not that manageable actually. This information, the dataset was quite big because it contained a lot of information about each playlist, about updates, and also the songs and the respective songs. And this is, of course, nice to have, but pushing all this information out to our clients or having it on our clients and working on it would have been a big problem. Going back to Ole's presentation previously, where it were users and items, in our case, it's playlists and songs. So we worked this data and made it to be just a playlist, just containing the songs. So on this side, we have the playlist ID. On this side, we have the playlist, the song ID. And this makes it possible for us to actually do some training, and it also fits into the bipartite graph structure. And it also makes it possible for us to handle this information because this was the regional data set was too big for our computers to handle. In total, it was 60 gigabytes of data, text data, over 1,000 files, and we worked this into a sparse representation of an adjacency graph, an adjacency matrix, with a test data set where all the clients had the same test data, but they had their own training data sets. And compressed, this was 10 megabytes, which was quite easy to actually download. It would have been even faster to download if it wasn't for the university computers or the network storage facility. And we also did some more cleaning on this. We actually removed some connections in this graph because it became too heavy. So we only songs that have more than 2 connections we kept. But this still means that our data set that we worked on had 857,000 songs in it. And 63 or almost 64 million connections or edges. We did this in a 90-2 split, so we kept even 2% of this data is quite a lot for testing, or enough for us to test with. We also did some reshuffling, so this is not information from different playlists could be spread out over different clients. So this is not completely a recommender system. We're using the recommender system idea, but this is not like it's one computer, 3 playlists. The information could be spread out. And we also saved the other information, of course, because when we have the recommendation will be a number, and we want to know what that number represents in the end. So we save that on the other side in this nice Parquet format, which saved a lot of space. Since this the federated learning is very dependent on the data and the models on the machines, on the local clients, we thought it would be nice to actually say something about the issues with that, especially me, because I like to break things. Because when you don't have control over the models that you're training and the data that you're using, it opens up for malicious use. So basically, some of those ideas, this is some ideas about this, but civil attacks. If you have a lot of friends and you want to influence the model predictions, you could of course do that by creating fake accounts or getting a lot of people to do the same thing. You could of course manipulate the model before sending it, manipulating the global model. You could of course poison the data by adding stuff that shouldn't be there. And of course you could, not that interesting perhaps in a song recommendation system, but you could also of course acquire information from the model on if identities of people or songs in this case represented in the data. So just a few words on the issue, and there are links to information if someone wants to know more about that. So now about the deployment.
Yeah, so as you might notice, we kind of focused a bit more on actually trying to scale it. So here we have the 3 rooms in normal computer rooms at Linköping University, each containing about 15 or 16 computers each. And then the nice little picture up there is supposed to represent the 5 computers, virtual machines we also had in Umeå. So the question then was, how do we kind of do this practically? Because we don't want to go to all of these computers, log in and start them. That would be very non-scalable in a way. So first we kind of looked, what do we have to do on one client then? So we kind of cooked it down to one bash script, which basically is everything. It has to be run on each client. So what the bash script then basically does is that it creates a nice environment so we don't break anything else on these computers, because they are actually lab computers that are used basically during the whole day and even when we conduct experiments. And then we download the data. Of course, this would not be the true in the federated learning, but somehow we have to simulate it. So we then use GDAM to basically download both the authentication file from Fedem and the data file. And then we kind of unpack them, install Fedem, and tell Fedem then where should they look for the data. And then we say, well, start. But then we want to do this on scalable level, so multiple clients in a way. So what we then do is basically we made another script, which then we just say all our hosts. And then for each host, we create a unique bash script where it states which data to use, which authentication, the name, and some other relevant info. And then we create a tmux session, because tmux is then a tool where you can actually start several sessions kind of at one time, and then you can go in and monitor them so you see what happened. We don't want to start them and then leave them there. We kind of want to see, does everything go as planned or not? So the next thing to do is then in that session, we simply SSH into the host, and then we run the bash script that is on the last page. So the nice thing with tmux then is that you basically get all the different sessions if you're up. Then you can simply choose that, well, let's go into one of these computers and see what happens. And then you can simply follow what happened here. Has the training started? Is it installing? Is something breaking? Or if you want to shut down the process, you can simply do that as well. So this is then what we actually did. So as stated, we used the Fedem interface, manage the server side. And for us, this worked very good. There were, of course, some things that could be improved, but like in general, it worked as expected. So what we basically did is we uploaded a compute package and a seed model. So the compute package is basically everything a single client needs to do training. The seed model is the first kind of model. And then we connected all the clients. As you can see here, we checked through the interface if they're online. So in total, it ended up to being 50 computers. One of our computers, for some reason, just crashed. We have not quite figured out, but 1 out of 50, 51 is quite okay. And we could kind of, as long as we generate some more data, it would be super easy to scale this to 100 or 200 computers. About there, I think our storage would kind of die. Then we would have to take other measures. But in theory, it was very easy to scale further. And what it ended is basically, as stated, 10 rounds and with 1 epoch in each. And of course, we get some results, and we can follow this. And I don't think this is actually the kind of doesn't say that much, that the model kind of worked good, I would say. But interesting was that you can actually see that the training time was often quite different depending on the computer. And somehow maybe even if something else was happening on the computer also kind of had an influence. But so then the actual kind of result from this then. So from a playlist then. So for example, this playlist named Chill, we get recommendation of songs. So here we have then the top 3 ones. So the top one then from this playlist will be the Chainsmokers. Then our model simply outputs a Spotify link to that song. Let's see if this works. So 2018, I think this was a popular song then.
They didn't have.
Yeah, this was another song.
Yeah.
Yeah, it didn't quite sound like the Chainsmokers, right? Yeah.
I think this is familiar to most people.
Probably put the next.
Yeah.
This is the next one.
Yeah. And we see the Chainsmokers were really popular.
Yeah.
But also they kind of the playlists that for some reason we have randomized here are, as you can see, quite same type.
I wanted to show playlists that were the size range of 15 to like 25 because some of them were like 200 songs and that was difficult. And then they were really mainstream and got the same recommendations basically, because some of these were also very, very popular songs.
Yeah, I think that was it from Mark's side. Thank you.
Ask away.
So is sort of the recommendation of the playlist based on the name of the playlist? What exactly, or what does the title have to do with the playlist?
Nothing.
Nothing, okay.
So you get this embedding some way at the start. So every user might can get an embedding, and we just find similar embeddings. So the name is not included. It could be.
There's no semantics at the moment.
No.
Okay.
No.
That's just added because just to make the presentation more interesting. I think that the next one is also very new, fun. We can all recognize that name setting as well.
Yeah, at the back maybe.
The embeddings have to be simple.
I think you need the embeddings of the users and items to be the same so that you can take this dot product. Is that what you were asking, right?
Yeah, and when you're starting when you use
Yeah, I'm not totally sure. I guess it cannot be just random because then everything would just be noise. You need to space out these embeddings, initial embeddings. I'm not certain how they do it, but it cannot just be noise. Then everything would just be noise. Everything would be brown, which often happens in graph neural networks. Everything just goes to brown. Nothing works. So some kind of spacing.
And for the items, you said that you use the items. Was that the only thing you did?
Yep. We only needed the ID of the playlist and of the songs.
So you didn't choose the.
So no other features is included, no other properties of the songs or the playlist now. Purely embedding.
Just a technical question, because on one slide you said that we're using Python version 3.9 to 3.12. Two questions about that. First, why did you choose a fixed version?
No, it uses for this, but we install it on when we start the client, we ask it to have pinpoint times. Yeah, but I don't think it matters. You could use anyway.
Okay, but why did you then write 3.9 to 3.12?
I think it's what the Fed kind of works for.
Yeah.
Recommendation.
And we tested 3.13 and it didn't work.
Yeah.
By accident. We tested it.
So at some point I had to start all these sessions, not like that, but do it in by 14 windows. So that was quite annoying.
Yeah, but otherwise, something said only one machine didn't work, and
Yeah.
so that's quite impressive. So you made the scalability, I guess.
Yeah.
And they, like Lukas mentioned, there were students having labs during our testing. We just hoped they didn't notice, and we haven't had any English speaking right now.
I think we're not mentioning this at all, okay?
I think
I was wondering, so you had these different clients and you were also talking initially about that there might be different devices. I was just curious, like with your training, did you like run one effort of the data on all clients and then waited for all clients to complete?
Yes, or we had a maximum time. So if one client for some reason times out or crashes, they just wait. I think we said 5 minutes.
Yeah. In Fed, then you set the maximum time to wait.
Yeah.
Okay, so it could also be that it hadn't crashed, but that it was just slow. And
No, but we checked it, but because we are teamworks, we could went in and see it.
And that something had
So something had happened.
okay. So they were all within like 5 minutes.
Yeah, but like I
think
think
we had-
actually in 10 rounds
I think we had some clients
that didn't run all rounds. They somehow didn't manage. But then they were into the next one instead.
Okay, was that kind of, were those parameters still saved or was it just like?
I think they just show it.
Okay.
Yeah. And this is a property of Fed.
But then it's also kind of nice because then you can always add one more client to the 11th round or 10 more clients and they would participate in the 11th round.
And this is because there's some data packet loss in the network communication end, or?
It could be limitation of the hardware resources.
Okay.
Yeah, because your computers mainly run on CPUs. And these have GPUs of different kinds, because all school has a really nice GPUs. And the Limpa has really bad GPUs.
We do it on purpose. Yeah.
But then your data sets are all equal size.
Yes.
Kind of, you don't know then. Yeah, but yeah.
More or less.
So each client has like a bunch of playlists and a subset of songs for each of their playlists, or?
They have a mix of playlists. So they're not all, the playlist 5 is not all of the same.
Okay.
The information could be spread out over several clients, which makes this not a complete recommender idea, but we wanted to use the data for a federated learning system, and the results, aggregated results, becomes the same.
So I guess the main idea is that each client will have some partial playlist and a partial list of songs, and then they share and then they improve each other's experience.
Yeah. If you just would divide it straight off, it would be like 20,000 playlists per client, and that is more than I have on my Spotify.
Have you considered like other applications of these kinds of federated recommendation on embeddings beyond playlists and songs? What are maybe some natural?
There exists many like for any web shop or movie recommendation like Netflix or whenever you go into web shop or there are tons of practical examples.
Choice of courses.
Yeah.
Some courses. It's dangerous.
We ran on the complete data set at one point, and Ule's computer crashed. Yes. So it would have been too much for one computer to handle.
Yeah.
But playing up, it went fine.
Yeah. Quite fast.
Using the lovely Fed.
With such a heterogeneous systems of GPUs, did you notice any difference? Because I mean, I've noticed that GPUs aren't really deterministically come to the same conclusion, so to speak.
No, but then you also, I think here, you have the different running times. Yeah. But then also, I think, because we talked to the Federated guys a bit during the process. Yeah. And so it should vary, it varies for some reason, but also the number of epochs you choose to run on each client is, you want to keep it down, because the more epochs you do on each client, the more kind of niched it gets.
Yeah. And these numbers could also be influenced by students actually using their computers for serious course stuff.
Serious-ish, this is more
serious. Yeah, of course, but
But Are there any other questions? Okay.